All right, let's get started with 4.6, rational functions. So a rational function is a situation where we have a polynomial divided by another polynomial. So it could be written as the polynomial n divided by the polynomial d. Both of them have to be polynomial functions. So just a situation where you have one polynomial on top of the other in a fraction. So here's an example, x plus 1 over x squared minus x minus 6. So the first thing we are going to do in this section is figure out the domain of these rational functions. So remember, the two rules of domains are you cannot square root a negative and you cannot divide by 0. So in rational functions, we do have division because we have a denominator. So we're going to say that the denominator cannot equal 0. So in this situation, we need to factor. So we'll say what multiplies to 6? Negative 6 and adds to negative 1, negative 3 and positive 2 cannot be 0. So x cannot be 3 or negative 2. All right. And so this says express the domain in interval notation, and we're not going to do that. So scratch that off. We can leave our answers just like that. All right, your turn. See if you can find the domain of this rational function. So denominator, x squared minus 3x minus 4 cannot equal 0. Factor, x minus 4, x plus 1 cannot equal 0. So x cannot equal 4 or negative 1. All right, so let's try it again when the domain of a rational function is the set of all real numbers. So sometimes you can use every x. So x squared plus 9 cannot equal 0. X squared cannot equal negative 9. All right, so we've learned that if you square root a negative, you can get imaginary numbers. But for domain, when we're talking about domain, we're talking about just the real numbers. So x can be all of the real numbers because the only things it can't be are imaginary. So for this, we're going to say the domain is all real numbers. Your turn. Hopefully this was a quick one for you. X squared 4 cannot equal 0, so x squared equal negative 4. And so x cannot be plus or minus 2i, which means it could be any real number. All right, let's talk about vertical, horizontal, and slant asymptotes. So to talk about these things, and actually get rid of slant. We're not going to do that in this section. Just vertical and horizontal asymptotes. So first we need to figure out what asymptotes are. So asymptotes are lines that the graph of a function approaches. So these are lines that we get really, really close to. You've seen this before on a graph where you have a line coming down like this, and it gets really, really close, and it keeps getting smaller and smaller and smaller and closer to the x-axis, but never actually touches it. In this situation, the x-axis would be your asymptote, a line that you get really close to, a line that you approach, but never touch. So here's an example that might help us make sense of this. Suppose a football team's defense is at its own 8-yard line. There's the end zone. Play football, that's the area you're trying to get to. And we are 1, 2, 3, 4, 5, 6, 7, 8 yards away. All right. The other team gets an offsides penalty that results in a loss of half the distance to the goal. So we were at the 8-yard line, so we get to go half closer. So all of a sudden, 7, 6, 5, we're at the 4-yard line. We're getting closer. All right, it happens again on the next play. So then we get half as close again. So now we're at the 2-yard line. And this keeps happening over and over and over again. Will we ever reach the end zone? We won't, because half of 2 is 1. Half of 1 is the half-yard line, and then the quarter, and then the 8th, and then the 16th. But we would never, ever, ever actually get to the end zone. So in this case, the end zone would be our asymptote. That line would be the asymptote, because it would be a place we'd get really close to, but never actually touch. All right, so let's learn how to find vertical asymptotes. So a vertical asymptote is going to be the same, almost the same, as our domain. So it's going to be any zeros of your denominator after it's been properly factored. And we'll see an example of that in a second. For this example, we're just going to factor our denominator. So 6x squared minus x minus 2. And so our AC here is negative 12. And our B is negative 1. So what gets us to negative 12? about 4 and 3. And to get to -1, we would need the 4 to be the negative. Let's put this over 6x. And so this reduces to -2 over 3x. And this reduces to 1 over 2x. And so we have 3x minus 2 and 2x plus 1. For asymptotes, we're going to say equals 0 because we want the line of the actual line of the asymptote. So 3x minus 2 equals 0. And so x equals 2 over 3. 2x plus 1 equals 0. X equals -1/2. Those are your vertical asymptotes. Your turn. Give it a shot. All right. In this case, our denominator has an AC of -30, AB of -1. So that's going to be 6 and 5, where your 6 is the negative. Put these over 2x. And then we have x minus 3, 2x plus 5 equals 0. So x minus 3 equals 0. 2x plus 5 equals 0. X equals 3. X equals -5 over 2. All right. Now, sometimes we're not in lowest terms. So here's the answer down here. We're going to look at that in a second. But let's go ahead and factor our denominator. So x cubed is 3x squared minus 10x. We can pull out an x. X squared minus 3x minus 10. That gets us x. And this will factor to x minus 5 and x plus 2. Now notice that in the numerator, we also had an x plus 2. So what happens here? The x plus 2's cancel out. So what are our asymptotes? X equals 0 from here, and x equals 5 from here. So the vertical asymptotes are x equals 0 and x equals 5. X equals -2, which is what we would have gotten from this one, is not in the domain, and there's not a vertical asymptote there. There is a hole there. All right, so this is extra credit type material here. There's a hole at x equals -2. What that means is the graph would be going right along and just jump right over when x is equal to -2. In class, we're going to look at some graphs of these. But just for now, know that extra credit, if you want to think about it that way, think about where a hole would be. And that's the places where your factors cancel. All right, your turn. Give it a shot. All right, so let's find our vertical asymptotes. If we factor the denominator, we would have x minus 4 and x plus 3. Be careful here. We do need to factor the numerator to make sure nothing cancels. So we have x, we just pull out an x. We'd have x minus 4. So look at that. The 4's cancel, so our only vertical asymptote is x equals -3. That's our vertical asymptote. We do have a hole at x equals 4 from the cancel factor. All right, horizontal asymptotes, fairly straightforward. You just got to follow the rules. So here's the big rule here. This is easier said on this slide here. So when the degree of the numerator is less than the degree of the denominator, so if you had an x squared on top, x squared on top over x to the 4th, if the numerator is smaller than the denominator's degree, then y equals 0 is your horizontal asymptote. You're done. If they are the same, if you have an x squared, let's say 5x squared over a x squared, if the degrees are the same, then you divide 5 over 1, and that is your asymptote. And if the numerator is bigger, x cubed over x squared, there is no asymptote. Take a look at some examples. So on this one, 1 is smaller than 2. Those are the degrees. So automatically on A, y equals 0. On B, 2 is the same as 2. So we're going to say 8 over 4 is your asymptote. So on this one, 8 divided by 4 is 2. Y equals 2 is your horizontal asymptote. And on the last one, 3 is bigger than 2, so we have no horizontal asymptote. There's an M in there and a P. Asymptote. Your turn. See if we can find our horizontal asymptote. All right, hopefully you said y equals -7 over 4, because 3 matches 3, so we divide the 7 over the -4. All right, that'll do it. We'll see you in class.